We thought we'd be missing James. I mean, we're so glad James is here. Okay. And let's get started from current slide. Well, there we go. All right. Now, we're not doing that yet, but we will continue. Let me just to keep from bothering people up and down the hall. I'll close that. Where we're starting today, if there are no questions, any questions? Where we're starting today is the vocabulary from 2.5. We got right up to that, but didn't quite get the chance to do this. So here we go. Number 1. This is on page 182, Chapter 2, Polynomial and Rational Functions. 2.5 is zeros of polynomial functions. And number 1 is the blank blank of blank states that if f of x is a polynomial of degree n, where n is greater than 0, then f has at least 1 0 in the complex number system. That's a pretty lame but essential, I don't want to say the word because that's one of the words in the blank blank of blank. What would that be? You flip back one page. The summary. Oh, clever you if you were able to remember that. Okay. Fundamental theorem of algebra. Gauss, I believe, proved that. Okay, number 2, another 3 blankers. The blank 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 states that if f is a polynomial function of degree n greater than 0, then f has precisely n linear factors. F of x equal a sub n out front, okay, x minus c1, x minus c2, x minus c3, all the way down to x minus cn, where c sub 1 through c sub n are complex numbers. Remembering that real numbers are complex numbers, but these include those with imaginary parts. So what's that one? The blank blank blank. Oh, look at that one. It's there too. Linear factorization theorem. Okay, number 3. The test that gives... This is going strange things here. The test that gives a list of possible rational zeros of a polynomial function is the blank blank test. Rational zeros test, how cleverly named. Okay, and number 4. Sorry. If a plus bi, where b is not equal to 0, is a complex zero of a polynomial with real coefficients, then so is its blank blank, which is a minus bi. What is that called? Oh, how many times did we repeat that? Say again? Yes, but it's complex conjugate. You can have conjugates that's a plus b times a minus b. Those are conjugates. A plus bi and a minus bi are complex conjugates. Number 5. Every polynomial of degree n greater than 0 with real coefficients can be written as a product of blank and blank factors with real coefficients, no imaginary parts here, where the blank factors have no real zeros. And a hint on this one, not going to be necessarily n of these factors. It will be something quite often less than n. A product of blank and blank factors with real coefficients, no complex, no imaginary parts, where the blank factors have no real zeros. Earth to class, come in, please. Page 157, where it talks about factors of a polynomial. The block that says that. It's not that hard to read. Okay, that's the first two blanks, where the quadratic factors have no real zeros. Yeah, perfect. Okay, now what that means, remember we just said the linear factorization theorem means every polynomial degree n greater than 0 has n complex factors. Okay, but now those complex factors may be real. This one's saying that you can break it into either real or linear factors or real quadratic factors, because all those quadratic factors that can't be factored, okay, that have no factorization, those are what produce your conjugate pairs. So those are your imaginary parts, so they always form quadratic when you multiply them together. So as long as they got real coefficients, you can do all linear and maybe a few quadratic factors if the quadratic factors have no real zeros. That's all you're going to be responsible for factoring is just the real parts. So they could be quadratic. Number 6. A quadratic factor that cannot be factored further as a product of linear factors containing real numbers is blank over the blank. Tammy, right? It's right about the same place we had, just right below the block you read from last time. Blank over the blanks. Oh, it must be Monday. It must be cold. Our brains are frozen. Oh, that's it. Okay. Second, irreducible over the reals. Got it. All right, number 7. Well, this never end. Okay. The theorem that can be used to determine the possible numbers of positive and negative real zeros of a function is called the blank blank of blank. Descartes' rule of sign. Perfect. And number 8. A real number C is a is a blank bound for the real zeros of F when no real zeros are less than that C, and a blank bound when no real zeros are greater than that C. Say again? Upper and lower, okay, except in the reverse order, lower and upper, okay. The real number C is a lower bound for the real zeros of F when no real zeros are less than that C. And it's an upper bound when no real zeros are greater than the C. Perfect. And y'all got all the homework exercises. You've done them every one and got them all right, so we're ready for any questions on 2.5 before we move to 2.6. Okay. And Jeanette didn't want to hear any of those vocabularies, so she just came in. Okay. All right. I think I got everybody when they came in. All right. So we're still in Chapter 2, Polynomial and Rational Functions. And up to this point, up to 2.5, we were all in the polynomial part. Now we get to the rational part. Okay? What in the world do we mean by rational functions? Anyone got an idea, a clue, a hint, a guess? Ratio, exactly. And what does a ratio mean? Something. What did you say? Say again? Yes, something in a fractional form as a ratio, and a fraction is always something divided by. So these are quotients of, guess what kind of functions? Polynomial functions. Excellent. So what we're going to do, our objectives here, find the domains of rational functions. What were the domains of polynomial functions? All real numbers. Okay? For rational functions, not necessarily. Okay? We'll find vertical and horizontal asymptotes of rational functions. Now, the vertical asymptotes will be directly related with the domain, by the way. We'll sketch the graphs, surprise, surprise, in this book, of rational functions, okay? We'll sketch graphs of rational functions that have slant asymptotes. We're going to skip that one. I'll show it to you, but you're not going to be responsible for that. We'll use rational functions to model and solve some real-life type situations. We will do that. So we'll introduce. Okay. A rational function is a quotient of polynomial functions that can be written in the form, this is your rational function f of x, your n of x and your d of x are your polynomial functions. N of x, d of x. Now why would they name it n and d? Numerator and denominator, very creative, aren't they? Where n of x and d of x are polynomial functions, and d of x is not the zero polynomial. Zero itself is a polynomial. D of x can't be that one. Okay. Now, that also leads to what we were talking about before, limitations on domains and also vertical asymptotes. We'll still be dealing with that d of x. Okay? And in general, the domain of a rational function of x includes all the real numbers. We always start there. We assume all real numbers unless there are some x values that make the denominator what? 0, because you can never divide by 0. Okay? Much of the discussion of rational functions will focus on their graphical behavior near the x values excluded from the domain. So in other words, near those places where x is equal to 0. That's where we will focus a lot of our graphical attention there. Okay? Whoa, jumping right into it. Find the domain of this function. F of x is equal to 1 over x. What do you think the domain of that function would be? All real numbers, except 0, because x equals 0 would make that undefined. Okay? Now, it says discuss the behavior of f near any excluded value, x values. It's very bad. No. Okay, what happens there, if x is approaching 0 from, you want it from the left or from the right? I have to say it backwards. From the left, okay, this way. So there negative x is coming in closer and closer to 0. So give me a negative x fairly close to 0. Say again? Negative 1. Okay, what would f of x be? 1 over negative 1 is? Negative 1. Okay, we got it. That's not too bad. Give me one closer to 0 than negative 1. Negative 0.5. Okay. What would be 1 over negative 0.5? Negative 2. Okay. All right. Right? 1 over 1/2 is? Okay, so that would be that. Get me something closer to 0 than negative 1/2. Say again? 0.1. Okay. What would f of x be if x were negative 1/10? Negative 10. All right? Negative 1 over negative 1/2, 1/10 would be 1 divided by would be flip that one, and you get negative 10. Okay, give me one closer to negative 0 than that. The negative 1/10. Negative 0.01. Good. Negative 100. What would f of x be then? Negative 100. Okay, where's that one seem to be going? The closer you get to 0 is going toward what we call negative infinity. Okay? It's going south so fast. The closer you get, the further it goes to toward negative infinity. Okay, how about from the other side? from the left-hand side. As you get closer to 0 there, where do you want to start? Second? Someone say something, I heard. 0.75, okay, which would be 3/4. What's 1 over 3/4? No. Think in fractions, let's make it easier. 1 over 3/4 would be 4/3, exactly, okay? Give me something closer than 3/4. Closer to 0. Say again? 1/5. What's 1 over 1/5? 5. Ooh, okay. Something closer than 1/5. 1 what? 1/6. What's 1 over 1/6? 6. Okay. Something closer than that. Say again? 1/10. What's 1 over 1/10? 10. Okay. Where are we going? Up. The smaller the fraction is, the larger the result is, right? So the closer you get to 0, to that excluded x value, that's what you have to exclude, x equals 0, then the more you're going to sum infinity. At least in this case. Okay? So let's see how they do it. Because the denominator is 0, when x equals 0, and the domain of f is all real numbers except that, except x equals 0, where your denominator makes it, the whole function undefined. Okay? So you got that part right very well, very good. So, to determine the behavior of f near that excluded value, okay, evaluate f of x to the left, they start on the left and the right of x equals 0 is indicated here. And they started with x equal -1, and they got f equal -1. We got it too. -0.5, that's -1/2. That became -2, -0.1. Someone was reading the book, weren't they? Okay. And then we go to -10. -100 was -100. -1,000 was -1,000. The closer you get to 0 from the negative side, this is going toward negative infinity. Nowhere else. This is no turning back. Just keep dipping lower and lower. Now let's approach 0 from the right-hand side. Okay? And they start over here. Clever, I guess. But see, I guess this is right. 1 would produce 1. 0.5 or 1/2 produces 2. 1/10 produces 10. 100 produces 100. 1,000 produces 1,000. Yeah, the closer you get to 0, the more that's going toward positive infinity. Does not have a limit. It just keeps rising forever. Now think about this. Well, I think they'll show the graph. Okay, note that x approaches 0 from the left, and f decreases without bound, and as it approaches 0 from the right, it increases without bound. Okay? So you got it going in this way. Do you see why there's not a value x equals 0? These are going that way, these are going that way. Can't possibly ever meet. Okay? No way at all. And there's the graph of it, and they just begin to show that just keeps going down, down, down. This keeps going up, up, up. No way there's going to be any value x equals 0. Okay? Any questions on that? Okay? Now, they do have a checkpoint like they do after just about every one of these examples. Oh, by the way, I missed saying this. Example 1, you can see larsonprecalculus.com for an interactive version of that type of example. And then the checkpoint, you also go to larsonprecalculus.com for audio-video solution to that checkpoint. Okay, make sure I don't destroy my computer here. All right, next thing we're going to talk about are first the vertical asymptotes. Okay, and then we'll talk about horizontal asymptotes. Just to give you a hint, let's go back one slide. You see one of each here, whether you realize it or not. A vertical asymptote is a place where a vertical line where the function cannot ever exist. So as soon as you say x cannot equal 0, you can plug in, I'm going to leave my red here, you can plug in, and there's a vertical asymptote. Notice it approaches, the function approaches it from the left and from the right, never touches it, never crosses it. Now, this one also happens to have a horizontal asymptote. Now, there is a difference here, but not in this problem. Here the function comes along, and when x gets extremely large negatively, it's approaching 0. It doesn't ever reach there. When it gets extremely large positive, it's approaching, the y value is approaching 0. So those are your horizontal asymptotes, okay? We didn't say it here. That's what we're going to be discussing here. Okay? In example 1, oh, here they are going to say it. The behavior of x near x equals 0 is denoted as follows. This sort of looks familiar, doesn't it? Remember our end behavior back early? I think that was 2.2 maybe. Okay? When you looked at what happens as x goes to positive infinity, x goes to negative infinity, what your function is doing. This time, we're letting x approach your place where it's not defined. Okay? And what is it doing when it approaches that from the minus side? This one is going downhill. What does it do as it approaches x from the 0 from the positive side? It's going to positive infinity. So the same way you express in behavior, we're going to express function behavior near an asymptote. Okay? I like to put this first, because that's the independent variable. As x approaches 0 from the left, f of x is going to negative infinity. As x approaches 0 from the right, f of x is going to positive infinity. Okay. Sorry. Now, they say it the other way. It's same difference. So the line x equals 0 is called the vertical asymptote of the graph. That's a completely correct statement. What I like to do, let's go back to the original expression right here. As soon as you have f of x equal 1 over x, I like to comma what we first said, x cannot equal 0. Any place where you can have a not equal to, that's where you put your vertical asymptote. Most of the time. We're going to see one exception to that, but that's where we'll put that. So I like to express it as where x can't be 0 rather than where x is 0. Okay? Both ways of saying it are fine. X cannot equal 0, you have a vertical asymptote, or the way they say it here, at x equals 0, it can't touch it, so you have the vertical asymptote. Whichever way you want to say it, I'll give you credit for it. But just know that if you got a not equal sign there, that indicates a vertical asymptote most of the time. Now, they show here we also have the horizontal asymptote, but we haven't discussed that yet. Maybe that's going to be next. Here we go. From this figure, you can see the graph of f also has a horizontal asymptote. The line y is equal to 0. Now, that's okay to say that way. It's okay to say x equals 0 too. But it's perfectly all right. That's how I say it. Okay? Because it doesn't mean that y can't be 0. It means in the long run, that's where y is approaching. So this is your end behavior again. This is just like your end behavior. The y is always going to a plus or minus. Well, no, it's not. It's going to some value as x goes very large negative or very large positive. So the x's of the thing, they're going to infinities, minus infinity, plus infinity. You have to figure out where the y is going. Okay? In this case, y was going to 0. So here's how I would say that. As x approaches negative infinity, your f of x is going to 0. As x is approaching positive infinity, your f of x is going to 0. Okay? F of x approaches now. See, for polynomial functions, all these would be infinities, not with rational functions. Sometimes they're going to infinity, sometimes they're not. Sometimes they're going to 0, sometimes they're not. They may be going to -3, 14, whatever, but it won't necessarily be going to an infinity. Okay? That's why the graphs are important. But see, this also helps you figure out how to do your graphs. So it's one way or the other. So here's the definitions of vertical and horizontal asymptotes. The line x equal a is a vertical asymptote of the graph of f when as f of x is going either to positive infinity or negative infinity as x equal a. X approaches a either from the left-hand side with the minus sign or from the right-hand side, that would be with the plus sign on the a, superscript. Okay? The line y equal b, that's perfectly okay to say that, is a horizontal asymptote of the graph when f of x approaches b as x goes to positive infinity or negative infinity. Now, I've said it a couple times, but I haven't really explained why the difference is. I don't mind calling this y equal b. I like to call this x cannot equal a because it can't ever touch it. Because y equal b, it can equal b. In here, not out there. Out there, it's approaching it. But in here, it could cross b several times. In fact, y could even do this. Just cross it forever, but get closer and closer to it. So it's not that it can't equal b, it's that it's getting closer and closer to b, the larger and larger x goes to either negative or positive. Eventually, as x approaches positive infinity or negative infinity, the distance between the horizontal asymptote and the points on the graph approaches 0. They may have crossed earlier, but the further you go, the closer they get. So here are some vertical and horizontal asymptotes of the graph of 3 rational functions. Now I'm going to go on and give you the hints on how to determine this. Okay, I think you know how to determine what the vertical asymptote here is. F of x equal 2x plus 1 over x plus 1. What would be the clue on what's your vertical asymptote? X plus 1 cannot equal 0, where your denominator cannot equal 0. And if you write that down that way, that's how I like to write it. You don't have to. The book does where x plus 1 is equal to 0, but it can't be 0. Okay, so x plus 1 is not equal to 0. Solve that inequality. You do what? Subtract 1 from both sides, and you get x cannot equal -1. And there it is. X cannot equal -1. All right. There's your vertical asymptote. That's always how you get your vertical asymptotes. Okay? Now, keep saying this. There is one exception. We'll get to that a little bit later. They sort of sneak it up on you. So I'll try to warn you when it's coming. The vertical asymptote is the way I like to do it. X cannot equal -1. Ever. It cannot touch it. Cannot cross it. Cannot. Okay. Now, for the horizontal asymptote, see, the vertical asymptote is always an x can't equal something. Horizontal asymptote is where a y is equal to something, even when D'Angelo shows up. Okay? All right, good deal. Now, remember, the key is x is going to infinity, getting larger and larger and larger. Okay? Now, as this numerator, as x goes to infinity, this is getting very close to infinity, right? Getting bigger and bigger and bigger. Which term governs then? The 1 or the 2x? Where the numerator is going? The 2x for sure. X is bigger and bigger. That part's getting bigger. 1 stays 1. Okay? It doesn't change.
Hey.
All right. It's Raquel, right?
Yes.
Good deal. Okay. All right. So, how about in the denominator here? Which term of these two terms you think is going to govern when x gets very, very large, negative or positive? The x or the 1? The x, of course. Well, guess what now? If you think back to our polynomial functions, when we're talking about end behavior, what do we use to determine the end behavior? The leading term, right? Same thing here. Except, because this is a rational function, what we look at is the ratio of the leading terms. And what's the ratio of 2x over x? 2. There's your horizontal asymptote. Y equal 2. The ratio of the leading term, that determines what your horizontal asymptote is. What your vertical asymptote is, what your denominator can't be 0. Figure out what values of x would make that 0. That's what you have to disallow. Your horizontal asymptote, look at the ratio of the leading terms, and that will guide you to where, if you do have a horizontal asymptote, where it's going to be. Okay? Now, let's look at this one. Vertical asymptotes. Where do we look? Yeah, your denominator. And where is the denominator equal to 0? X squared plus 1. Where is that equal to 0? It's never equal to 0. Because any real number you put in here for x, you're going to square it, and it becomes positive. If that was a positive number, it's more positive, or it's positive. If it's a negative number, it's positive. Okay, when you square any real number, it becomes positive. Add 1 to it, and it's more positive, right? So this has no zeros for the denominator, so no vertical asymptotes. Do you see any? Not a 1. Okay? Now, how would you determine the horizontal asymptote? The ratio of the leading terms. But the leading term, the only term in the numerator is a 4. And the denominator is x squared. Now what happens to that value there when x gets very, very large, positive or negative? 4 over a huge number. Give me a huge number. Make up a huge number. 100. So 4 over 100 is 0.04. Give me a bigger number than 100. 1,000. 4 over 0.004, okay? Guess where that's going? Closer and closer to 0. Positive or negative, okay? Because no matter what sign this is, that's going to be positive. So this is approaching 0 from the positive side. That's approaching 0 from the positive side. So it does have a horizontal asymptote, y equals 0. Okay? Now, how about this one? What determines your denominator? What determines your vertical asymptote? What happened in the denominator? Can that denominator ever be 0? At x equal, or x can't equal 1. Because if x was equal to 1, that would be 0 squared, which is 0. Okay? So therefore, x cannot equal 1. So there's your vertical asymptote. How about your horizontal asymptote? Whoops. Whoa, wrong direction. Okay, here we go. Again, this time I would probably multiply out that denominator. So it would be 2 over, anyone can square x minus 1? Help me. Help me. Square x minus 1. A little louder. X squared minus 2x plus 1. What's the ratio of your leading terms? 2 over x squared. This is just like last time, isn't it? Only it's 2 over x squared rather than 4 over x squared. As x is larger and larger and larger, that y is going to 0 from both directions and going to 0 from the positive side. So it's up here and up here, okay? So it is going to 0. So your horizontal asymptote is y is equal to 0. Does that make sense? Yay or nay? All right, good deal. Now they're going to do each one of them separately and do the same thing we did. The graph of alphabet. Okay, don't get up. Okay. All right. The graph of alpha of x is equal to 1 over x in figure 221, and the graph of alpha of x equal 2x plus 1 and x plus 1 are both called hyperbolas. You don't really need to know that, but it is, they're both true, okay? A parabola, they're curves that basically form mirror images of each other in opposite directions. They don't have to be in quadrants like this or that. They could be like this or that. As they get the closest they get is somewhere along here, and then they get further and further away. Okay, those are called hyperbolas. Okay, so I don't know why they brought that up here, but it's perfectly fine. Okay, if you go back here, this is also hyperbola. This is in this direction and that direction. Okay, that's also hyperbola. These are not. Now, don't mistake this for a parabola. It sort of looks like one, but its tails flip up. The parabola keeps going down. Okay? These almost look like hyperbole. They're not quite what you consider hyperbole. These are getting closer together. These are getting further apart. They have more of a hyperbolic appearance anyway. So those are called hyperbolas. And again, not a real big issue here. Later, you'll find that. All right, so let's look at our vertical and horizontal asymptotes of a rational function. Sorry, my nose itches. Must go have company. My dog will be happy. Okay. Let f of x be a rational function, just like we said before, a rational function, a ratio of a polynomial function in the numerator and polynomial function in the denominator. This polynomial function in the numerator, a sub n, x to the nth, plus a sub n minus 1 times x to the n minus first power, plus jack these down, and finally get to a sub 1, x to the first, a sub 0 times x to 0, which is 0. That's your numerator polynomial. Your denominator polynomial may have a different exponent. So we'll call it may have different coefficients as well. So we'll have b sub m times x to the nth power times plus b sub m minus 1 times x to the m minus first power, plus count down the powers here until you get b sub 1, x to the first, b sub 0, x to 0, which is 1. Now, the n's and n minus 1s and stuff on the coefficients, they are only markers saying this is the coefficient when x is raised to that power. This is the coefficient when x is raised to that power. Those are just markers. These are powers, so those are important, you know. These are part of your problem, okay? Now, so n of x, and here's the key. Where n of x and d of x have no common factors. They sort of snuck it in there, and are going to spring it on you later without warning, okay? So I'm going to give you the warning now. So one of the first things we do when we have a rational function is see if we can factor the numerator and factor the denominator. Now, these are big, old, hairy-looking polynomials. They may be hard to do, okay? But you're going to have to do them anyway. So you use your rational zeros test. You do everything that we've learned in 2.1 to 2.5 and find that factorization if you can. Remember, you can have some irreducible quadratics. That's fine. Get them all to factor as much as possible. And if when you factor numerator and denominator there are common factors, eliminate them to some extent. You have to remember they were there, but here's the deal. They will not produce, just because you have, say, x minus 3 is one of the factors down here. If you have x minus 3 as one of the factors up here too, you take them out. This one doesn't produce a vertical asymptote of x equals 3 because you eliminate it. What it does produce is a hole in the graph there. You still can't have x equal 3, but it's not going to produce a vertical asymptote. So that's why I said every time we said it, most of the time, they will put on vertical asymptotes if a factor down here is 0, but that's only if there's not a factor up here to cancel it out or divide it out. So that's why they say no common factors. The graph of F has vertical asymptotes as long as they have no common factors at all the zeros for D. That's why you factor them, because you've got to find those zeros. The graph of F has one or no horizontal asymptotes. See, F can have a bunch of vertical asymptotes. If this is give me a number for M. Make up a number. 2. Okay, that's going to have up to 2 vertical asymptotes. It may not. It may only have 1, or it may have none. Okay? Give me a bigger number. Bigger than 2. 4. Then it could have up to 4 vertical asymptotes. Wouldn't have to. It could have 3 or 2 or 1. Okay. Actually, only 2 or 1. Okay. 2 or 0. Okay. Because when you factor it, you know, the common factors. Okay. Now, so the graph can have multiple vertical asymptotes depending on how many factors it has in the denominator. Okay? Those are the zeros of the D of F. Every one of those, as long as they have no common factors, every one of those zeros is a vertical asymptote. Now, the graph of F has either one or no horizontal asymptote. It can't have 2 or 3. Only one or none. One or none. Horizontal asymptote. Determined by comparing the degrees of your numerator with the degrees of the denominator. And they put this little thing in here, and it's all perfectly well and good, but if you just look at this ratio, it'll tell you exactly what's going to happen. When the n is greater than or less than the m, that means this will be when you divide out the x's, you'll have no x's left and at least 1 or 2 x's down here. Well, that's going to produce a horizontal asymptote of y is equal to 0. Because you're going to have a number, just like we did before, a number over something with x in it. And that's going to go to 0. This x is very large, positive and negative. So when n is less than m, the graph of F has a line y is equal to 0. And it is the x-axis as the one and only horizontal asymptote. When that n is equal to m, remember that 2x plus 1 over x plus 1, the n's were both 1. N and m were both 1. So the x's cancel out, and you have the ratio 2 to 1. Then it has the graph has a line, y is equal to the ratio of those leading coefficients. Okay? And that will be your horizontal asymptote. And if this denominator, n, is greater than the m in the denominator, the numerator degree is greater than this, you have n's up here and no m. You have x's up here and none down here because if n is greater than m, these all cancel out and these do not. So now it's going to infinity, positive or negative, depending on the sign of the leading coefficients, the ratio of the leading coefficients. So then it has no horizontal asymptote. Don't worry about the rest of it. That means it's going to an infinity. Some infinity, one over the other. Okay? And you see that held true back here too. When the n and m were the same, horizontal asymptote x equal 2. When m was greater than n is 0, m is 2, no horizontal asymptote. Same thing here. N was 0, m was 2, no horizontal asymptote. I'm sorry, set it back. Horizontal asymptote of y is equal to 0. If this had been x squared over 4, then you would have no horizontal asymptote. Same here. So if the degree is greater than the numerator, no horizontal asymptote. The degree of the denominator is greater, 0 is your horizontal asymptote. Oh man, the old gray cells aren't working. So let's do example 2. Find all the vertical and all the horizontal asymptotes of the graphs of each of these functions. Doesn't say we have to graph it, we may graph it. How about vertical asymptotes for the first one? What are we looking for? Say again? Denominator, and what about the denominator? Yes, x minus 2 cannot equal to 0. Okay? Well, what can we do with that expression there? That's 1, okay? We can write it correctly. That's what we can do with it, okay? Put a 1 there, okay? Now, where do we go from there? Factor. How will that even factor? How? X plus 1 times x minus 1. Okay, if that product can't be 0, what does that tell you about either one of those? Neither of them can be 0. So this gives you x plus 1 cannot equal to 0. It also says and, not or, and x minus 1 cannot equal 0. Remember, when we're looking for zeros, we say or. Either that 0 or this one. This one, if you're looking for the vertical asymptote, neither one of those can be 0. Because if either one is 0, your denominator is 0 and you can't have it. Okay? So what does the first one give you? X cannot equal negative 1, and this gives you x cannot equal positive 1. So you have two vertical asymptotes, one at negative 1, one at positive 1. Okay? So there's what I call your VAs, vertical asymptotes. How about your HA? How do we get your horizontal asymptotes? For that first one. How many could you have? Horizontal asymptotes? Only one or none. No options. Okay? So, what would be your horizontal asymptote? What do we look at? Horizontal. Say again. Ratio of your leading terms. And what is that? 2. Because your x's go out 2 to 1. The horizontal asymptote is, well, how do we express that? I raise you 3. Never mind. Y is equal to 2. I can't write. Okay, y'all are competing with me now, aren't you? Okay. Cut it out, folks. Okay. I'm tired of coughing. I can't get my eraser to erase. All right. Erase too much. At Y is equal to 2. One and only one horizontal asymptote. If you got it through, I'll take it any time. Good deal. What's that? I doubt it. We're not going to finish this. Yeah. Okay. But we can if you want to. I mean, sure, I'll do anything. Okay. No test Thursday. We got to finish this section first, and right now we're on page. Never mind. Okay. Now, so we found the vertical asymptotes. Y is x equal, not equal to negative 1, not equal to positive 1. The horizontal asymptote, y is equal to 2. Okay. Now, how about the B part? What would you recommend we do first? It doesn't matter whether you do it first or not. What would you do first? Say again? I couldn't hear. B part. Is what? Okay, what about the denominator? What you going to do to it? Say again? Set it, okay. X squared minus x minus 6 cannot equal 0. The book doesn't equal to 0. Either way you want to do it. What will you do with it next? Factor it. And what would that give you? X minus 3 times x plus 2. And that product still cannot be equal to 0. Sorry about that. And what does that tell you? X cannot equal 3, and x cannot equal negative 2. Two vertical asymptotes, you got them. Those are your VAs, vertical asymptotes. How about your HAs? Now, we failed to do something that we probably should have done. What was that? Factor everything in sight. We factor this denominator to be x minus 3 times x plus 2. What happens if we factor the numerator? X plus 2 times x minus 1. And what did I tell you they were going to do? They're going to sneak up on you and do this to you. X plus 2's go out. So that does not mean that x cannot equal minus 2 is a vertical asymptote. It's not, because there are common factors. Now, that does leave something open to you, so that now your vertical asymptote is only x cannot equal 3, but let's go back and do the horizontal asymptotes. What can we do with that? You go back to the original. Don't do what you factored. Well, it works there too, but what do you do? Ratio of the leading terms, and that is y is equal to 1. Okay? Very good. Now, they're going to show you the graphs of these, and hopefully you'll see what happens there. X can't equal negative 1, x can't equal 1, y is equal to 2. Let's look at that graph first. Oh, I've got to erase all this. So, any questions before I delete this? There. Oh, okay. I just deleted it. Okay. The horizontal asymptote here was x. Y is equal to 1. Y is equal to 1. The ratio of the leading terms is 1. Okay? Now, for that rational function, the degree of the numerator is equal to the degree of the denominator. Yay. That only bothers you on horizontal asymptotes. Leading coefficient, the numerator is 2, the leading coefficient, the denominator is 1, so the y is equal to is a horizontal asymptote. Just look at the ratio of leading terms. That does it for you. To find the vertical asymptote, set the denominator equal to 0, or I'll say it not equal to 0, however you say it. Resulting equation is that. When you factor, you get that. When you solve, you get that, except I say not equal to, they say equal to. You say tomato, I say tomato, I don't care. And those are your two vertical asymptotes. I like to say not equal to, remind me I can't touch it. Okay, so it has two real solutions, x equal negative 1 and positive 1. So those are vertical asymptotes. Okay, this is what it looks like then. Okay, x can't equal negative 1, x can't equal positive 1, y is equal to 2. Okay, could you graph it from there? No. You need more information. Okay, now, they aren't telling you how to do this yet, but I'm going to go and give you a hint. Okay, what you do here. Okay, one other thing I would do for this problem is say, where is your x-intercept? In other words, where is y or f of x equal to 0? Well, that's only going to be where your numerator is equal to 0, right? Where is your numerator equal to 0? At what value? 0, 0. So there's your y-intercept. It also happens to be an x-intercept. Okay? Now, that was your y-intercept, okay, where the numerator was equal to 0. Your x-intercept is where y is equal to 0. No, I'm sorry, the y-intercept is where x is equal to 0. So you just put in zeros here. And what do you get in your numerator? X equals 0. 0 in the denominator, minus 1. Well, 0 minus 1, that's 0. So your only intercept is going to be right there. Okay? Well, that tells you it touches the graph right there, no problem there, but we have absolutely no idea where it goes from there. So what you have to do then is take some test points. I would pick some test point to the left of this one, something in between -1 and 0, something in between 0 and +1, and something between 1 and 2. Well, greater than 1. These are test points, okay? Plug those into your function and see what happens. And if you plug in, say, x equal -2, this would be 2 times -2 squared is 4. 2 times 4 is 8. Divided by 2 squared is 4, minus 1 is 3, 8/3. Well, 8/3 would be somewhere up about 2 and 2/3. And sure enough, that's about where it is. So that's positive. Now, once you have a point here, as opposed to down here, once you have a point here, you know that it's approaching your vertical asymptote going this way, your horizontal asymptote going this way. Has no choice. Once you know one test point, you can determine where the rest of the function is going. Now, down here, you have to choose one between -1 and 0, like -1/2. That's going to be a sort of a pain, but it's still doable. -1/2 squared is 1/4. 2 times 1/4 is 1/2. In the denominator, you have a 1/4 minus 1, which is -3/4, right? Well, I don't really care what the magnitude is. I just know that it's negative. So it's somewhere down here, and you can figure out what the magnitude is, but it's somewhere down here. Well, once you know that, figure out what happens between 0 and 1. Well, say 1/2 again. That would be a 1/2 up here. And this would be, again, a -3/4 down there. So it's negative again here. Well, now, it can't turn around and go back up, because if it did, it would have another 0. And we know it doesn't have another 0. So this has to be continuing down toward this vertical asymptote and continuing down toward that. Once you have a test point, you know where it's going from there. When you go x equal 2, say, a test point there, that would be 4 over 8. 2 squared is 4 times 2 is 8. And this would be 4 minus 1 is 3. Same thing as before, 8/3. Right there you are, somewhere right about there. So you're in this quadrant here, so it has to stay in that quadrant. It can't come over here. It doesn't tend to go over. So you see, at that point, you have to have test points. You can't just look at it and say, oh, this is where it graphs. Just because a book seems to do that, you can't do it. You have to do test points. But one test point in each area will tell you where it's going from there. Okay? Now, they'll get to that later, but they just sort of threw it up there as if you were supposed to know that. You weren't. Okay? Now, the B part. That was A. Here's the B part. The degree of the numerator is equal to the degree of the denominator, so it's going to have a vertical asymptote, and that's going to be, the ratio is going to be 1, so y equal 1 is your horizontal asymptote. To find any vertical asymptotes, first factor, and you should have said this at very first, factor everything in sight, okay? And if you factor this and factor that, you find out there is a common factor of x plus 2. Once you eliminate the x plus 2, then you know your vertical asymptote is x can't equal 3. Okay? I already determined your horizontal asymptote was 1. Y is equal to 1. Okay? So what you do, where did they get a -2? I don't know. That's a -3. No, it's a +3. Goodness gracious. Did they ever get that screwed up? Okay? And they got it wrong in the book too, didn't they? Am I doing something wrong? No.
Would it go into?
Wait. Okay. They're right. Let me tell you what they're doing. Okay. Let me erase it all. Okay. what they should have said at this point right here, x cannot equal -2 and x cannot equal 3. But when you eliminate this, that eliminates x not equal -2 being your vertical asymptote, but that's still a condition. X still can't be -2 because that would make your denominator 0. It's just that it's no longer an asymptote. This is your asymptote. This is your VA. This is the HIG, the hole in the graph. Okay, not the book doesn't call it that. I just made that up. That's your hole in the graph. Where when they eliminate like this, this becomes your hole in the graph. This becomes your vertical asymptote because that did not get eliminated. But that is correct. X cannot equal -2, but that's not your vertical asymptote. Okay? But by setting the remaining denominator equal to 0, then x equal 3 is your vertical asymptote. It should be saying x can't equal 3. Okay. Oh, they didn't sketch that one, did they? Shame on them. Okay. Let's go back and sort of sketch that one quickly. This is a shame because they should have done that. Okay. Let me find some place to do it. Okay, let's do it here. All right. Here's your vertical axis, your horizontal axis. Your vertical asymptote was x cannot equal 3. 1, 2, 3. Okay, I'm going to put, is it almost time to go? Okay, let's do it as quickly as possible. Here is your vertical asymptote right there. Your horizontal asymptote was y is equal to 1. So let's do a 1 here and do your horizontal asymptote there. Okay, now, let's go back here. Let's say, where is, when you say x equals 0, that's going to be your vertical asymptote, right? I mean your y-intercept. So x equal 1, 0, y-intercept. That's going to be a positive 1/3. So y-intercept is positive 1/3. There is positive 1/3 right there. Okay? Whoops, that's not what I want. No, wrong. Okay. No. I keep hitting the wrong icon. X equal, or y is equal 1/3 is right there. That information right there is enough to tell you that the function is going to be down in this quadrant of those asymptotes. Okay? When you set, go back up here and say where your numerator is equal to 0, this numerator is x equal 1. So x equal 1, right here, you also, that's a x-intercept. Well, these two tell you the function here has to be down here. It's going to approach the horizontal asymptote as you get smaller x's, approach the vertical asymptote as you get close to the vertical asymptote. Now, what you have to do is pick another point out here, say x equal 4. Okay? Oh, I messed up something. Remember, x can't equal 2. Remember that? X cannot equal, oh, messed it up again. X cannot equal -2. -2 is over here. There's your hole in the graph. Okay? They gave you this example, but they didn't explain it very well. Okay? There's your hole in the graph. Because it can't equal -2, but it doesn't have a vertical asymptote there. If you pick x equal 4 out here and plug that in, going the wrong direction. Let's do it right here. X equal 4. Let's use this one right here. 4 minus 1 is 3. 4 minus 3 is 1. So that's going to be 3. 1, 2, 3. That tells you your function's right there. Okay. That's not a slant there. That should be part of that. So that's how you draw this function. When you have one that you eliminated by division, that gives you a hole in the graph. When you have one you don't eliminate by division in your denominator, that gives you a vertical asymptote. Where x is equal to 0, That's going to be your y-intercept, where y is equal to 0. That's going to be your x-intercept. They're going to get to those later. We'll stop right there because we're out of time. There is a checkpoint. You can go to larsonprecalculus.com and follow up on that. 2.6 homework exercises. This is a long section, folks. You can do either 5 or 7. They're both at Calc Chat. 7's at Calc View. You can do any of the odds, 9 through 15. They're all at Calc Chat. 15's at Calc View. You can do, we'll hang off sketching until next time. So just go through 15 for now. Good deal. Any questions? I've already been telling you hints about sketching, but we'll get to do it formally later. Good deal. Had a lot of absences today. I don't know if it's a holiday, the cold weather, or what, but I'm glad y'all were here. Yeah, it is. Good deal. Any questions?